This is a class related with good problems related with columns. Columns are actually load members, and we will be looking two of the main calculations that we can do with columns. However, the calculations and properties of wood are very extensive. We can have tension, compression, bending, shear, toughness, and many other things. And we will go very fast to explain what they are, but we will only do calculations in two of these elements. First, we have tension, that strength that is parallel to the grain. What is important when we are speaking about trusses, how the truss will be supporting a weight that is not perpendicular but parallel to the grain of the material, because as we can look here, the material is in the same direction of the particular loads that are applying, that will be just transmitted to the supports. Tension perpendicular to the grain is very important in design connections and of wood building, like diagonal brace elements and post-beam construction in countries like Japan. Compression that is parallel to the grain is important when we speak about columns in wood buildings that are supporting the weight in the top of that column, where the grains will be parallel, as you can look in this picture. Compression that is perpendicular to the grain is important in connections when we have pieces in two opposite directions. The bending strength is more, and that is one of the ones that we will calculate, MOR, and is a load that is peak in the long beam that will be carried. That is an accepted criterion of strength, but it's not true stress, because it's proportional to the limit of the material. That depends on an assumption that it will deform according with a linear elastic range. If the material is not elastic enough, that will not happen, and wood usually is quite elastic. The shear strength is when we have a load in the top of the material, and the parts of the material, like in this case, that we have a board that is composite with several layers, will move around. We also have a shear strength that is related with the part of the wood that is against to the next piece of wood. And that depends of the grain of the wood. The conditions will be different. Toughness is related with the work that is need to break a small specimen of wood with when we have an impact load. And that is important when we are putting some nails or elements that put two pieces together. We have resilience, that is about energy. When the timber bend in an elastic range, side hardness is important for flooring. When we have a good floor, it needs to be hard. If not, we have denting. And work with a maximum load, that is the energy that the material have related with a bend that is very slow. However, the most important properties, and are the ones that we will be studying for columns, are two. First, module of elasticity, or MOE, that is a resistant to bending. When we have a beam, remember, moment is the most important element and will cause bending. Well, we want to look how this material will bend and will change of dimension, and bending will be a measure of the elasticity of this material. And this is the MOR. After, the elasticity also can be perpendicular parallel to the grain, and that is what is called the Young module, and is a resistant to elongation of shortening of a specimen of wood under tension or compression, when we have a load in the top of the beam, or in our case, in the top of the columns. Well, let's look also another very important property that we already looked in the past, and you study in Structures 1, we study in the review, that is stress and strain. Stress, obviously, is a particular force that is related with the force divided by the area. And we can have a shear stress if we think in the shear divided by the area. That is something that we already did in the past. Strain is the change of elongation. When we have a strain, we will have the change of the length of the material divided by the original material. And the shear strain will be something very similar when we have the angle of the deformation by the original angle that the material has. Well, we can look here at normal stress and strain and shear stress and strain, how the material is moving and is becoming more elongated, or how the material is just having a degree of change, as we can look here. Stress and strain have very important connotation when we speak about an axial load. Axial load is the load that you put in the top of a column, for example, and will make the material to have some particular stress. And that stress will be it will have a relationship between the strain and the strength of the material until the moment that the material crush or break. Below the proportional limit, we have a relationship between both of those elements, stress and strain, and that is related with the Young model. Here we have an example that we already looked in the past that is very simple. We have a piece of material that is a beam of a column, sorry, of 2 by 2, have a normal length of 6 feet, and we have a load of 8,000 pounds in the top of this particular material. And this load obviously will cause some kind of compression in the material. What will be the stress? Very simple. We divide the load by the area, and we have load that is in pounds and area that is in inches. We have a result in this particular case of 2,000 psi, pounds per square inch. The strain. The strain is a change in the dimension of the material. Well, we have a material that originally have a dimension of 6. Let me try to move here again and draw it. One second, please. The material have a length of 6. And when we put a load, it became a little bit smaller. It became 5.99. Usually all those numbers are calculated with dimensions that are very small. Well, the change of length in our particular case is simple. We have the original length that we have, that is 6, and I'm sorry, let me go back. We have the original length that is 6, and that will be a negative number, and we will look how change, what is the dimension of change. Well, the material became a little bit smaller. Well, we have the dimension that the material got attained, that is 5.9928 minus 6. And that will divide by the real dimension that the material have originally, that is 6. Well, the change of dimension, that is the strain, was 0.0012. It's the change of the dimension in relationship with the original dimension. The Young model is very simple. It's stress divided by strain. And we can look here, that is 2000 divided 0.0012, that is 1.67 multiplied 10.6 psi. What happens inside of the material? It happens that we already know that there is a deflection. The material became deflected in the top of the beam. We'll have some compression in the inferior part. We'll have the material that will extend. And in the center, that is the neutral axis, nothing will happen. And that will allow us to understand what is the maximum compression stress and the maximum tension stress. The compression stress will be maximum in the top of the surface and the tension in the inferior part. Well, we have some observations when we do this kind of information, and we like you guys to read this in the slides when you study and understand what's going on with the beam. We already spoke what happens in the neutral axis, what happened up, what happened down the beam. Well, the first calculation that we'll be doing today is model of elasticity of MOE. It's a static bending test that will think about what happens in the loads that are traversing that particular element. Well, we imagine that we are cutting that material in several places. We know that in the center, nothing will happen, but we know that things will happen, especially in a very strong way in the superior and inferior part of that beam. Well, we will have a lot of compression in the superior part and a lot of tension in the inferior part, and the material will start to deflect. And that deflection is caused because of the moment. And at the same time, when the material deflects, in the superior part, we'll have a lot of shear, and in the inferior part, a lot of tension. In order to calculate the model of elasticity of any piece of wood, we need to understand what are the beam dimensions, the span, the load, and the deflection. This model of elasticity depends on the material that we're using, and the formula is P, that is the load, multiplied by L, that is the span. The span will need to elevate at 3 because it's an important number, and it will be divided by a number that is a constant, 48. Let me go back, I'm sorry. 48 multiplied by the moment of inertia that depends on the beam size, wide, and deep. And you will receive this moment of inertia, and you will be able to calculate it, and D, that is the deflection. Well, let's go with the first of the problems. Example number 1. Here we have a piece of red oak stick. It's 50 by 50 by 762 millimeters. Usually because the dimensions in the material are very small, millimeters are used to calculate these elements. It supports at each end for 711 millimeters of span. I mean, the material is 762 millimeters, but the span, that is the number that we need, is 711 millimeters. It's load at the center. The load is gradually increased. That is important because if the load came all of the sudden, we have different conditions. When the load is 6,680 Newton, the deflection in the midspan is 6.6 millimeters. What is the MOE? Well, this is the piece of wood. 711 millimeters is the span, 711. The material is 50 by 50, it's a square. And the MOE had a formula that you will have in the test, and we just need to put the force, that is 6680 newtons, multiplied by 0.711 millimeters, that is elevate at 3, divided by 48, that is a constant, multiplied by I, that is 6680, and D, that is 0.711. We receive all the data. We just need to plug the information, do all the resolution of this equation, and the MOE is this one. This MOE, we will approximate this, have an approximation of this number of 14,600 for the next problem. Just to approximate that one, because we will use the same data for the next problem. In the next problem is very similar, but we want to know how much this piece of wood deflect. Well, we have the same piece of oak, of red oak, that is 0.075 square piece, and with the same type of quality of before, the MOE will be 14,600. Is an approximation of what we got it. Well, this is a number that we will receive in the test. And we will place this material between two roof beams, 1.27 meters apart. We will put in the top a weight of 1,360 kilograms, that is the same of 13,350 newtons. And we will hang this from the center, and we want to know how much the specimen will deflect. Well, we have the same formula of before. MOE is equal to PL elevate 3 divided 48 by ID. But we need to rewrite the formula. We will take D from this particular formula. When we take D out of the formula, what will happen is that this element will pass in the other side of the formula, and well, PL3 will be the same, 48 that was divided will be there, and MOE will move and occupy the place of D. Well, we substitute all the elements in the formula. We write this one, we write the second one, that is L, and we divide by 3. We multiply by 48, and we have here I, that is the moment of inertia that we receive, and we have finally this particular last element that is related with the information of the beam. And I'm sorry, I told you that you received the moment of inertia. No, you received the MOE that we already calculate, 14,000. And for the moment of inertia, we take the material that is is a square, 0.075, 0.075. And as you know, always the most important is the height. Well, we take the base, 0.75, we multiply the base by the height of the material, that is 0.73, that is elevated to 3, and we divide by 12. That is a formula that we always use. And when we do auto resolution, we arrive at the conclusion that the deflection is 0.015. Usually the deflection is very small. If you have a big deflection, it's because you did a mistake, because normally it's a very small element, normally. Well, let's look at the next example. In the next example, we are not calculating MOE as before, we have MOR, that is the module of rupture. This is where we are supposed that the element will break. It's the static bending test. I mean, we put a load in a beam and we start putting more and more weight until that beam break. In the moment that that beam break is the moment that we have a rupture in the material. Let me go back, I'm sorry. We have a rupture and we need to do some calculations to understand when that happens. Well, MOE and MOR are the important elements when we calculate this kind of beams. For the model of rupture, we use a formula. Let me go back to show you. Imagine that we have a weight in the superior part when that material will break. Well, MOR will be MC, that is the maximum moment, divided by the moment of inertia. That is the formula. We can also rewrite this as the MOR is 1.5 multiplied by P, that is the maximum load during the test, multiplied by L, that is the span, and divide by the beam width and the beam height elevate at 2. Okay, this equation is valid only when we have a simple beam, support at the end, and load in the center, and all our problems will be of this type. Formula will change when we have different other loads, and they become a little bit complicated. Well, I think that this is an easy representation that will work for our understanding. Well, here we have a sample of red oak that is the same that we had in the problem before. And we need to calculate, let me go back here because I just passed this. Well, let's write this formula, understand this formula, and do the first of the problems. This is problem 3. It's very simple. We have a piece of oak, the same that we have in the sample 1, is loaded until it fell with a testing machine. The breaking load is 9,400. How much is the MOR? Well, we know when the material will break. It will be when we have a load of 9,400, but what is the more of this material, the MOR, the module of rupture? Well, very simple. We'll just substitute, let me go back again, sorry. We just substitute the information. 1.5 is a constant, P is the load that we know that is not 9,500, is written there. The particular dimensions of this material is a base by a height, and we know that the total is 0.711 because we had from before. That will be the length of the material. I'm sorry, the length of the material is 0.711, and after we need to divide by the base, that is 0.5, and multiply, by coincidence is a square, 0.05 elevated 2. And we resolve this, and the mole is 80.2 MPa. We can have the same type of problem with the same formula, but instead to understand what is the MOR and try to find MOR, we want to look the space, the span between this material. And what we can do in the same way. We can look what is the maximal space heater weight, the weight that that material will be working and will be applied in that particular span. And well, we just need to reorganize the formula and take out from the formula P. If we take P out of the formula, it will be like 1.5, and L that were two elements that were multiplying now will be dividing, and the rest will be the same. And well, we can work with this particular formula. If we take out P from here, P go in the other side of the equation, over there more go in this side of the equation, and that will be the new organized formula. We just need to substitute. You don't even need to memorize this equation because you will receive in the test, and you will be able to look in your slides because tests with problems are open book, as you know. Well, I don't think that will be difficult to make this substitution and just apply all the numbers and find a final result. Well, in the test, you will have several problems like the ones that we are looking, and you have finally to practice questions that will help you to understand a little bit more what we want in the test. We have an example 2, and you can practice these 2 examples using 2 particular type of wood with similar conditions, but different. And after, you can calculate the maximum space heater weight, I mean the maximum load, for 2 particular pieces of wood with different conditions. Thank you very much. This concludes the presentation.